In the course of the physics of solar energy conversion, we study today the diffusion transport. Diffusion is the stochastic motion of a particle. It's hopping randomly, and it doesn't go in a definite direction, but it's making a displacement nevertheless. So if we inject a density of carriers at the origin, then these injected carriers will start to move, and the distribution will spread out. And it will spread out according to a distribution function, depending on time, so that we can calculate the mean square displacement of a particle by integration of x squared. And such mean square displacement is proportional to time. So there is a definite flux from the origin away from it. And if we place here some characteristic distance, L, then the time for reaching such distance will be L squared over the diffusion coefficient D. From the stochastic equations for hopping between sites, which represents the random walk motion, we can make an average and establish an equation that describes the evolution of carrier density. Basically, this is that if we have a concentration with respect to position, so that if we have some distribution of carriers, then this will create a flux in the direction of the gradient, so that diffusion will tend to equalize the charge. And in conclusion, if we multiply by the charge, elementary charge, then the electrical current associated to diffusion is the product of the diffusion coefficient and the charge distribution gradient. We can put this also in terms of the Fermi level, because this distribution is represented by a Fermi level that is going away from the conduction band, so that a gradient of the Fermi level with an horizontal band will represent also diffusion. Now we consider recombination in addition to diffusion, so that an electron is doing a diffusional motion, but it has a probability to suffer recombination with a hole, and then we will have diffusion, but the number of electrons will be disappearing, so that if we inject here a continuous flux of electrons, the number will be decreasing because of the recombination as they move to the right. Now, this is the problem of diffusion recombination, and then it's interesting to find which is the characteristic distance that the carriers can move before they disappear by recombination, and this is called the diffusion length. The diffusion length can be calculated if we know the carrier distribution by solving the diffusion recombination equation, and then one can obtain that the diffusion length is the square root of the product of the diffusion coefficient and the recombination lifetime. Now we can analyze what happens then when we inject electrons into the semiconductor. So we have here the conduction band and the valence band, and now we inject the electrons right here at the left contact, so they are going to enter the semiconductor layer. What happens then? Well, there will be electrons and holes, there will be some recombination, so that there will be diffusion of the electrons to the right and also recombination. And how far they arrive will depend on the diffusion length. If the diffusion length is very short, then they will arrive inside a short distance. But if the diffusion length is longer than the size of the semiconductor thickness, then they will reach to the end, provided that here there is a reflecting boundary so that the electrons are not absorbed or lost here. Then in the long diffusion length, then we will have a good transport and the carriers will be homogeneously distributed inside the layer. But if the carriers get to the end and here they disappear, for example, for recombination at the surface, then even though the diffusion length is long, the carriers at the end cannot survive, so that they will be lost, and then there will be a bending of the Fermi level as well. Therefore, the diffusion length is an important concept for charge collection. It means that if we are going to generate electrons and holes by photogeneration, and we want to collect the electrons at this contact here, then the carriers generated inside can access the surface by diffusion only up to a distance of the diffusion length. After that, the carriers cannot reach the electron extraction contact, and there will be a lot of recombination in this region. This is a quantification of the diffusion length for electrons in lead halide perovskite with a diffusion coefficient of 0.1 centimeter square second to the -1. And the diffusion length will depend on the electron lifetime. At moderate charge densities, the lifetime can be considered constant. So it can vary from 1 nanosecond to 1 millisecond. And then the diffusion length in micrometers will vary from 1 to 100 approximately. So this is a long diffusion length, so that when it is longer than the solar cell thickness, we will have a very good charge collection. Diffusion in disordered media means that the electrons are going to find traps and disorder as they move. So there are other mechanisms. For example, this is the trapping at one level and the trapping, so that the diffusion is slowed down. And then we have the hopping close to the Fermi level, in which there is no transport in the band, but the electrons are moving from trap to trap, and this is called hopping transport. Then there are different cases. For example, if we have a shallow trap, then the carrier will be trapped and released very rapidly. But if we have a trap in the middle of the gap, this is a recombination center, so that there will be diffusion and recombination. And if there is an exponential density of states, so the electrons will be trapped and released with different rates, because deeper traps will trap them for longer time than shallow traps. We have seen so far two mechanisms for transport. One is diffusion, the other is drift in the electrical field, and we can combine them into equations for the current for electrons and holes, and these are called the drift diffusion equations. In a given situation, we can have the two mechanisms. For example, if we have a depletion layer at the surface, this will extract rapidly the holes in the electrical field, and in addition, so there will be a depletion layer for collection by electrical field, and then there is a deeper neutral region where there is no electrical field, and still here we have a region where we can collect the carriers by diffusion. That's the same thing for the semiconductor electrolyte interface, so that here we can bring the holes at the surface for oxidation reactions, and we can collect also the holes in the gradient of the Fermi level inside by diffusion. This concept of the gradient of the Fermi level is quite important. It means that we can combine the drift and diffusion into a single equation for transport using the expression of the Fermi level in terms of electrical potential and the density of charge. If we combine the two equations, we have the expression of the electrical current, which depends only on the electrical conductivity and the gradient of the Fermi level. So there is an expression that combines drift and diffusion. Using this general expression, we can interpret the transport in terms of the gradient of the Fermi level. So here we see two cases. At the left, there is a constant distance between the band with an inclination and the Fermi level. So this is drift transport with a constant carrier density. And at the right, the band is flat, but the Fermi level is inclined, so that this is the diffusion transport in a varying concentration. But if we see the shape of the Fermi level, it's the same in the two cases. It means that there is an applied voltage here related to the difference of the Fermi levels, so that we can express the general expression as the change of the Fermi level and the distance of the inhomogeneity. And this is basically Ohm's law. So that Ohm's law is not for electrical field, it's a general expression of the variation of the Fermi level in relation to the conductivity for a small perturbation of the Fermi level. From this interpretation of the gradient of the Fermi level that is required to drive a flux, we can analyze the different mechanism of losses of energy for the charge transport. So the first case is when we want to inject carriers. So this will be a very good contact because there is injection of electrons with no cost of the Fermi level. But if there is an interfacial layer or somehow the contact is not so good, then we will need a step of the Fermi level to enter the charge here. And there will be a cost now in the Fermi level and a loss of energy here at this interface. The second case is recombination. We inject charge. If there is a long diffusion length, then this charge will reach very far, and the Fermi level will be basically homogeneous. But if there is strong recombination, once the charge is injected, it will be lost in a diffusion length. So that, again, seeing the Fermi level, we can quantify the losses in the transport of carriers. Finally, if we inject the charge and we want to extract the charge at the other contact, here there is a very good transport with no cost, but in the other case, it's not so easy to transport, so we have to induce an electrical field. So there is this drop associated to the Ohm law, as we said before, that requires a voltage now to drive the carriers.